So I want to warmly thank the organizer for their kind invitation and for giving me the possibility to attend this meeting remotely. In this talk, I will try to summarize our current understanding about Type Ia supernova progenitors. I will review the classical scenario, discussing the limits and the related problems. At the end, I will discuss also more recent findings and their implications. So, as it is well known, we have no direct observation on Type Ia supernovae progenitors. So what we know is based on observational evidence and related theoretical deduction. Let me briefly recall that we do not observe hydrogen in the spectra at the maximum, and this means that progenitors have to be very evolved objects, such as carbon-oxygen white dwarfs. In addition, Type Ia explodes in galaxies of every typology, and they are the only supernovae in elliptical galaxies. This means that carbon-oxygen white dwarfs are present in both passive and active galaxies, and this because they are the endpoint of intermediate mass stars, which evolve on very short time scales. Interestingly enough, the white dwarf is a compact object, and this could help us to explain the short duration of the peak phase in the light curve. Unfortunately, white dwarfs are dead stars, and their fate is to cool down. However, the situation is different if they are embedded in interacting binary star systems. In this case, the mass transfer can rejuvenate the white dwarf, and the hypothesis of binarity is also interesting because it allows us to explain the delayed type distribution of Type Ia. In fact, in this case, the epoch of the explosion is fixed not by the evolutionary time of the star, but by the evolutionary time of the binary system, which could be very long, of the order or longer of 10 gigayears. At the end, the progenitor is completely destroyed. We don't have a combat remnant after the explosion, and the energy delivered during the explosion is employed to accelerate the ejecta. If we assume that the explosion is due to complete carbon burning up to iron peak elements of about 1 solar masses of carbon-rich material, then we can get rise of this evidence. So, according to this scenario, more than 6 years ago, Euler Fowler suggested that Type Ia supernovae are produced by the thermonuclear disruption of carbon-oxygen white dwarf accreting mass interacting binary system. In this way, the white dwarf can attain the Chandrasekhar mass limit. It can undergo a rapid compression so that carbon burning is emitted at the center in either generate physical condition. This is called the Chandrasekhar mass scenario for Type Ia supernovae. We have also another scenario, and it is the sub-Chandrasekhar mass scenario. And in this case, the explosion is driven by double detonation mechanism. Due to mass deposition, a helium buffer is piled up onto the white dwarf. When it becomes larger than the critical volume, a helium flash is emitted very strong. It turns into a detonation. The detonation determines the formation of a retonation wave, which focuses at the center and determines the local increase of temperature so that also the carbon-oxygen core detonates, and this produces the explosion. In order to reproduce a normal Type Ia supernova, however, the carbon-oxygen core has to be large enough and the helium buffer has to be small enough. Otherwise, a low energy, low luminosity with peculiar nucleosynthesis event will result. And for this reason, in the past, this mechanism was considered as not promising as the engine of Type Ia supernovae. So we have two different scenarios, the Chandrasekhar mass model, and in this case, the companion is could be another carbon-oxygen white dwarf, an helium star, or a normal star with a hydrogen-rich envelope, and the sub-Chandrasekhar mass model, and in this case, the companion could be an helium white dwarf, an helium star, or a normal star with hydrogen-rich envelope. Please note that in order for the white dwarf to attain the Chandrasekhar mass limit, it is if the companion star is a normal star, for instance, the accreted matter has to be nuclearly processed first into helium and then hopefully into carbon and oxygen mixture. Usually, the evaluation of what system would undergo in the future to a successful explosion binary population codes are used. These codes are very complex. They assume for each star formation episode the number of stars in a binary system, as well as the initial distribution of mass ratio in the binary systems and the initial separation. Then they derive from stellar evolution some information about how a star reacts to mass extraction and mass deposition. And by putting all these elements together, they find what system will explode in future. There are many inputs, and as a consequence, there are many uncertainties. The most uncertain quantities is the so-called common envelope efficiency, which determines the final binary system. And currently, we don't have any physical description of the common envelope phase. We have just order of magnitude estimates. And please note that in Type Ia progenitor systems, at least one common envelope episode has to occur in order to produce the carbon-oxygen white dwarf. The other very uncertain quantity is the so-called retention efficiency, which is the amount of matter transferred from the donor, which is effectively retained by the accretor. This quantity is used, computed in very accurate evolutionary models, but these models were computed with constant mass transfer rate, constant chemical composition, and in addition only for a short time duration. This means that the evolution is not computed up to the explosion. As a consequence, these models does not take into account the mass transfer history as well as the thermal history of the accretor. In addition, rotation is usually neglected, and we expect that rotation naturally arises in interacting binary system. Here, I reported the possible outcomes of hydrogen accretion as a function of the white dwarf total mass and the mass transfer rate. This map is from a work of our group, but similar results were obtained by other authors. And as it can be seen, for very low values of the mass transfer rate, the accreting white dwarf experience novae or nova-like flashes, and in this case, a large part, if not all the matter previously accreted, is lost by the system due to the combination of dynamical acceleration, binary interaction with the companion, and wind mass loss. For a bit larger values, the white dwarf experience mild recurrent hydrogen pulses. And in this case, the accreted matter is converted into helium, and then the helium buffer is piled up onto the white dwarf. For larger value, the accreted hydrogen is burned into helium at the same rate at which matter is accreted in a stationary state. And for definitively larger values, the mass transfer rate is larger than the rate at which hydrogen is converted into helium, and then a massive hydrogen-rich envelope is formed to the white dwarf expands, all the matter exceeding the rate at which hydrogen is burned into helium is lost from the system. Due to hydrogen burning, an helium buffer is piled up, and at a certain point, helium is ignited. The further evolution, however, is not computed by considering hydrogen accretion, but by considering models accreting helium-rich matter at the same equivalent rate. And for this reason, for instance, the presence of the hydrogen burning shells is completely ignored, and this produces different condition in the helium burning shell. This is for our work in 2014. Here I reported the limit for the expansion of the white dwarf. And as you can see, when helium is ignited, the white dwarf can undergo to very strong helium flashes. As a consequence, the white dwarf expands. A part of the matter previously accreted is lost from the system. So the retention in efficiency is smaller than 1. In 2016, Hillman and co-workers computed the long-term evolution of a hydrogen-accreting white dwarf with a mass transfer rate typical of the steady accretion regime. They followed all the recurrent helium flashes, and they found that the retention efficiency can vary between 20 and 70%. Please note that they adopted very massive white dwarf. The initial mass was 1 and 1.22 respectively. But usually white dwarfs are born with a lower mass, with the order of 0.8, 0.85. So we have to consider also the evolution from the original white dwarf up to at least 1 solar masses. In this case, the retention efficiency is lower than this. As a consequence, it is very hard that the Chandrasekhar mass scenario with a normal star as a donor could account for observational properties of Type Ia. In particular, supernova rate are not reproduced, and this because there are very few systems that could attain the Chandrasekhar mass. In addition, the delay time distribution cannot be reproduced because the evolution of the system occurs on a very short-term scale. So they can account only for a prompt component, not the long-term one. At the end, there is also a lot of circumstellar material, and then it is expected that some hydrogen in the spectrum at the maximum epoch. And at the end, there is a compact remnant, which is the dawn star. The situation is better with the double degenerate system, and this because there is no problem with of course, with the spectra at the maximum epoch. And according to the classical picture, carbon-oxygen white dwarf is accreted directly onto the white dwarf. This because, according to the simulation by Rasi or Shapiro, Benz, the less massive components disrupts, forming a sort of torus around the more massive one, and then matter flows directly into the white dwarf. In this case, the outcome of the accretion process can be very easily determined. If the mass transfer rate is low enough, let's say several times 10 to the minus 6 solar masses per year, then the white dwarf attains the Chandrasekhar mass limit, and carbon burning is ignited at the center. Otherwise, if the mass transfer rate is larger, carbon burning is ignited during the accretion, well before the white dwarf could attain the Chandrasekhar limit on the surface of the white dwarf. The burning front propagates inward, and so that the whole white dwarf is converted into an oxygen neon magnesium white dwarf. As a consequence, the final outcome, if matter is further accreted, is an accretion-induced collapse. This scenario has many drawbacks. For instance, the observational search of good candidates for an explosion has produced practically no results. And the other point is that in the classical picture, it is expected that mass transfer rate is very high. We, in the past, proposed a solution to this problem, and we suggested that rotation could play a pivotal role in determining the rate at which matter is accreted into the white dwarf. Rotation naturally arises in double degenerate system. And the mass transfer rate is high at the beginning, angular momentum is deposited, and the white dwarf becomes a fast rotator up to when it attains the critical angular velocity. In this condition, no matter can be accepted from the surface, and then the accretion comes to a halt for a while. Then the white dwarf contracts, and matter can be accreted again. This determines simply because by contraction, the white dwarf recedes from the critical condition. And this determines the decrease of the rate at which matter is effectively deposited into the white dwarf. Later on, when the white dwarf becomes a very fast rotator, it deforms and gravitational wave radiation are emitted. This stabilizes the accretion rate, and the white dwarf can increase its mass up and beyond the non-rotating Chandrasekhar mass limits. These results has been questioned, for instance, by Sayo and Nomoto, and they suggested that the white dwarf never attained the physical condition to emit gravitational waves, so there is no way to produce the increase of the white dwarf mass. But let's assume for a while that it is possible to produce a white dwarf as massive as the Chandrasekhar limit. The evolution is quite easy in this case due to the position of matter. The accreting white dwarf, the density profile along the white dwarf, as well as the temperature level increases up to when the physical conditions suitable for carbon burning at the center are attained. In this case, due to the high degeneracy, the carbon burning turns into a thermonuclear runway, and very soon convection sets in. The epoch lasting from the onset of the convection up to the explosion is usually addressed as the simmering phase of Type Ia Supernovae. During this phase, the ashes of carbon burning are mixed with the original material of the white dwarf, and at the explosion, the white dwarf is almost completely unstable for convection. However, as it can be seen, the density in the innermost zone becomes very large, and in this case, electron capture can occur. We are interested more than to electron capture to Urca processes. These are weak processes involving isobars, best isotopes having the same number of nucleons, but with different number of neutrons and protons. If the density is larger than a critical value, then electron capture are favored and the neutron each isobar is present. If the density is lower than the critical value, then the beta decays are favored and the neutron poor isobar is present. The critical density defined as a cold Urca shell. At the Urca shell, there is a continuum flow of matter from the neutron poor to the neutron-rich material and vice versa, during which process neutrino and antineutrinos are produced, and this carry away the thermal content of the white dwarf. So when in the original white dwarf, there are some of these isobars. When the density becomes large enough, electron capture occur and the neutrino are emitted. This produces a cooling, as you can be seen here. Later on, when carbon burning occurs, nitrogen 23 is produced, sodium 23 is produced, and sodium is involved in the sodium neon Urca shell. But in this case, the density at which electron capture occurs is definitively larger than the Urca shell. And in this case, the kinetic energy of the electrons released as thermal energy is larger than the amount of energy lost by neutrinos, and this produces a local heating. Then convection sets in so that sodium is produced, it undergoes the electron capture, and neon is produced, and neon is mixed outward. The further evolution is very complex because it is determined by the interplay between convection and Urca shell. What happens when material attains the Urca shell or goes through the Urca shell? We investigated this issue, and we find that if the Ledoux criterion is used and all the relevant energy sources and sinks are considered, then the innermost Urca shell stops convection. This means that the convective core remains always smaller than about 0.5 solar masses. In addition, the circulation of Urca isobars inside the core cools the core itself, and then a larger amount of carbon has to be burned, and this has important consequences on the neutronization of the explosion epoch. This model, of course, has some limitations, and the most important one is that we made use of the mixing length theory of convection to describe the zona stable for convection. This is a local theory, while we know that during the simmering phase, the mixing is turbulent. So in principle, mixing length theory should not be applied at all. And so the results could be, in principle, completely wrong. So this issue has to be addressed in the future with a tricky simulation, of course. The other interesting point is that the explosion density is very large. And in this case, during the explosion, high neutronized isotopes are produced, in particular chromium-54 and titanium-50. We make an exercise. We assume that all chromium in the solar neighborhood were produced by Type Ia supernova coming from the Chandrasekhar mass scenario. And we asked ourselves, what is the number of Type Ias coming from this scenario? The total number. So here are the results. We used the production factor of chromium-54 from our models. And what we found is that the Chandrasekhar mass scenario can account for no more than 26% of the whole Type Ia supernova exploding in the galaxies. And if we assume that the normal 1As does not produce does not overproduce chromium-54, then all Type Ia subluminous with lower luminosity comes from the Chandrasekhar mass scenario. We assume that the Chandrasekhar mass scenario could produce both normal and subluminous Type Ias. So this put some additional arguments against the double-generated scenario as Type Ia progenitors. Now let's turn our attention to the sub-Chandrasekhar mass model. And as I thought, once again, the initial... Sorry?
1 minute.
1 minute? One? Okay.
Yes, 1 minute.
Okay, I go very fast. We know that in this case, the mass transfer rate is can change as a function of time. And here, computed model with a variable mass transfer rate and the constant mass transfer rate. And as can be seen, by using model with the constant mass transfer rate, we can completely provide a wrong estimation about the mass at the explosion and then the possibility that the white dwarf could explode. I skip everything concerning rotation, but rotation completely changed the scenario, and I will comment only recent development about the double degenerate scenario. Packmore and co-workers suggested the violent merging scenario. In this case, the explosion occurs due to carbon detonation triggered by the violent heating of matter from the merging the component onto the more massive white dwarf, but this model is unable to reproduce normal 1As, and it is not clear if the detonation can occur at all in this system. An interesting possibility is the helium-knitted violent merging scenario where the companion is an helium white dwarf. In this case, detonation will result for sure because helium detonates very easily. And this gives rise to the so-called sixth model. And this model has many good things. In particular, the helium buffer is very small. The luminosity at maximum epoch depends only on the carbon-oxygen core mass. And in addition, white dwarfs are born with a very thin helium-rich layer. According to Shannon co-workers, all white dwarfs, realistic white dwarfs with mass in the range 0.9 to 1.1 solar mass have an helium buffer massive enough to trigger a detonation. The main drawbacks of this scenario are that, first of all, there are too many expected hypervelocity stars ejected during the explosion, and in addition, the fact that the presence of the companion produces a very asymmetrical distribution of the ejecta, a circumstance never observed in Type Ia and in supernova remnants. And at the end, I remarked that it is impossible to form white dwarf as massive as 0.9 solar massive, at least according to standard stellar evolution. So a solution could be a stable mass transfer episode before the occurrence of the merging. And this was demonstrated by Reuter and co-workers some years ago. But once again, these results were obtained with binary population synthesis code, so they are largely uncertain. At the end, it is not clear if the distribution of these systems could account for the observed distribution of brightest Type Ia supernovae. And I will stop here. Sorry for the delay.